Hello everyone. My name is Fatima Safana CH and together with Huda Rashid, we are here to present our seminar on two fundamental algorithms, Radix sort and breadth first search. I will be covering the first half, Radix sort, and Huda will take over for BFS. Let's get started. So, let's dive into Radix sort. Before I explain what it is, I want you to think about how you would sort a stack of numbered cards. Most of us would compare numbers and arrange them, but Reddit sort thinks differently. It never directly compares two numbers at all. That's what makes it special. Introduction to sorting and Reddit sort. First, a quick context on sorting in general. Sorting means arranging data in a defined order, either ascending or descending. It is one of the most fundamental operations in computer science because efficient sorting is what powers searching, database indexing, and countless other algorithms. We have different families of sorting algorithms. Bubble sort and selection sort are simple and easy to implement, but they are slow, of n square in the worst case. Merge sort and quick sort are better, of n log n on average, using strategies like merging or pivoting. But today we are talking about Reddit sort, which belongs to a completely different category. It is a non-comparison sort that works digit by digit. And as well we see, under the right conditions, it can outperform even merge sort. So what exactly is Radix sort? The word Radix means base, like base 10 in our decimal system. Radix sort processes numbers not as whole values, but digit by digit, units place, tens place, hundreds place, and so on. There are two key variants. LSD, least significant digit, starts sorting from the units digit and moves towards higher places. This is the most common approach for integers and is what we will focus on today. MSD, most significant digit, starts from the leftmost digit, useful in some string sorting scenarios. One critical dependency, Radix sort must use a stable internal sort at each pass. Stability means that when two numbers have the same digit at the current position, their previous ordering is preserved. The most common choice is counting sort. Without stability, the results from earlier passes would be destroyed. Now, let's look at how it actually works at a high level. The process is straightforward. First, find the matchment number in the array. This tells us how many digit places we need to process. Then for each digit place, starting from units, we apply a stable counting sort. We repeat this for tens, hundreds, and so on until all digit places of the maximum numbers are covered. When the last pass is done, the array is fully sorted. The key insight is each pass builds on the previous one because we use a stable sort. The order established in pass 1 units in respected in pass 2 10. Dry run example. Let me walk you through a concrete example so this becomes crystal clear. Our initial array is 170, 45, 75, 19, 802, 24, 2, 66. Pass 1. Units digit. We look at just the last digit of each number. 0 in 170, 5 in 45, 5 in 75, 0 in 90, 2 in 802, 4 in 24, 2 in 2, 6 in 66. We group them into buckets 0 through 9 and read them back out stably. Result 170, 19, 802, 2, 24, 45, 75, 66. Pass 2. Tens digit. Now we look at the tens place. 7 in 170, 9 in 19, 0 in 802, 0 in 2, 2 in 24, 4 in 45, 7 in 75, 6 in 66. Again, stable bucket sort. Numbers like 802 and 2 that have 0 in tens place come first, preserving their units pass order. Result 802, 2, 24, 45, 66, 170, 75, 90. Pass 3. hundredth digit. Finally, the hundredth place. Most numbers have 0 here. 170 has 1, 802 has 8. After this table pass, final result 2, 24, 45, 66, 75, 19, 117, 802. Note that the array is perfectly sorted and at no point did we ever directly compare 45 with 802. That's the power of Radix sort. Now, let's look at the algorithm formally. This is clean and simple. We start with the place is equal to 1, which represents the units digit. The while condition, max divided by place greater than 0, ensures we only loop as many times as there are digit places in the maximum number. Each iteration we call count sort on the current digit place, then multiply place by 10 to move to the next position. The count sort function extracts the relevant digit using array I divided by place mod 10. Dividing by place shifts the number right to bring the target digit to the units position, and mod 10 isolates just that digit. This is the key formula you should remember. Now, let's look at the complete sleeve implementation. The program has 4 functions: getMax, countSort, RadixSort, and printArray. GetMax. This function finds the largest number in the array. We need this to know how many digit places to process. CountSort. This is the most important function. It takes 3 parameters: the array, size, n, and the current place value. It creates an output array and a count array of size 10, one for each digit 0 to 9. First loop counts how many numbers have each digit at the current place using array I divided by place mod 10. Second loop converts counts to cumulative counts. This gives us the exact position of each element. Third loop builds the output array. Notice it goes from I is equal to n minus 1 down to 0. That means right to left. This is what makes the sort stable. Last loop copies output back to the original array. Radix sort calls getMax, then loops through each digit place calling countSort and multiplies place by 10 each time. Print array simply prints all elements of the sorted array. Main sets up our test array 170, 45, 75, 90, 802, 24, 2, 66, calls Radix sort, then print array to display the result. The most important things to remember, the right to left traversal in count sort is what makes the algorithm stable and correct. Let's now analyze the complexity. Time complexity. Radix sort runs in O of n multiplied by k time, where n is the number of elements and k is the number of digit places in the maximum number. Mathematically, k is equal to log base of max. Importantly, this is the same for best, average, and worst case. It's a very predictable algorithm with no bad inputs. Space complexity O of n plus k. We need an output array of size n and a count array of size k, 10 for decimal base. Comparison with bubble sort. Bubble sort is O of n square, significantly worse for large n. Radix sort wins decisively when k is more relative to n. For example, sorting a million 6-digit phone numbers. That's O of 6n versus O of n square. The difference is enormous. Then, the key takeaway, Radix sort's performance depends not just on n but also on k. If numbers have very many digits, the advantage shrinks. But for fixed length keys like IDs, phone numbers, or zip codes, it's extremely efficient. Like every algorithm, Radix sort has its strengths and weaknesses. Advantages. It's fast for large integer dataset when k is small. It's stable, so equal keyed elements maintain their original relative order. Useful when sorting records by multiple fields. It requires no direct key-to-key comparisons. And it's excellent for fixed-length numeric keys like employees' ID or phone numbers. Disadvantages. It requires additional memory. of n plus k extra space for the output and count arrays. It's primarily designed for integers or fixed length strings. Applying it to floating point or complex objects requires extra pre-processing. Performance degrades when k is large. If you are sorting 20-digit numbers, you have 20 passes, which may not beat comparison sorts, and it's less practical for variable lengths keys without careful padding or pre-processing. Applications and conclusion. Radix finds real-world use in several important areas. Database indexing, sorting large volumes of numeric records efficiently. Banking systems, sorting account numbers and transaction IDs. Telephone directories, sorting phone numbers or postal codes. And large-scale numerical data processing, anywhere you have millions of fixed-length integers. To conclude, Radix sort is an elegant, efficient, and stable non-comparison sorting algorithm. When your data consists of fixed length keys and k is small compared to n, it delivers consistent O of n multiplied by k performance and is often significantly faster than comparison based sorts for larger data sets. It trades some extra memory for a gain in speed, a worthwhile trade in many practical scenarios. With that, I will hand over to Huda for the second part of our seminar, Breadth First Search. Thank you.
Hi all, good morning. I'm Huda Rashid. I'm taking the topic BFS, Breadth First Search. BFS is a graph travels algorithm. It explores nodes level by level. It visits all neighboring nodes before it moves to next level. It uses queue data structure, like that is FIFO, first in first out principle. It's commonly used for searching and path finding. Next, we will talk about BFS algorithm steps. Um, it follows some steps to do the algorithm. And the first one is start from the source code. Yeah, first of all, it will start from the source code. Then it will mark the source code as visited. Like it can do any symbol markings that we can understand that we have visited that node. Then we will insert the source code into the queue. That is, the node we have visited will be inserted into the queue. Then we will remove the node from the queue. After writing the node, we will remove it from the queue. Then visit all its unvisited adjacent node. If we have a node A and it have two adjacent node B and C. After removing A from the queue, we will write B and C in, in them. After that, we will mark that one, first one B, that is in this queue it's B. It will as a, it will we use as a visited, mark them as visited, and we will remove that one from the queue. Then it's adjacent. Then that like that it will be repeating. It's very easy if we are looking at the example. Now let's do one thing. We'll just talk by using example. So this is an example graph to perform BFS travel cell. You can see node A is adjacent to D, E, B, and B is adjacent to A, E, and C. Like that, we can see it's adjacent to each other. So we have we to do BFS algorithm. We first take the node A. Then we will mark A as visited. So we can understand did we visited each node or not. So we will mark A, that is okay, like this. Here you can see I colored the node A, so you can understand we visited that, and I wrote this in the queue. Then we will look the adjacent of the node A. It's B, E, and D. Right. Then we will put that three adjacent node into the queue and we will mark them as visited. Okay. Then we will remove the first node in the queue. That is D. And we will look adjacents of B. That is A and E. That's already visited. So that we no need to write. That's already the queue, so no need to write. Then we will look E. E have B, C, and F. Then we have to write adjacent of the node E. E have D, A, B, C, and F. Already written D, A, B. Now we have to write C and F to the queue, and we will remove E from the queue. Okay. And also we'll mark C and F as visited, as shown here. Now we will remove the B from the queue and we will look the adjacents of B, that's A, E, C. That's already visited, so we will move to next one, that's C, and we will look the adjacents of C and we will write which is not visited, that's G, and we will write G to the queue and we'll remove C from the queue. Here we marked every nodes that's visited, and we can now remove F from the queue, and then we will remove G from the queue. That's after we will visited, we can remove one by one from the queue. And now we can see, if we look at the way it moves, we can see it. The result is like this. So the BFS pseudocode is BFS graph comma start, then create an empty q and mark start as visited, then nq, that's of start. While q is not empty, not equal to visited node. For each adjacent node of node, if it's not visited, then it will mark visited, then nq of adjacent node. So this is how BFS of pseudocode of BFS breadth first search algorithm. Next is the application of BFS. First one is shortest path in unweighted graphs. Like find shortest path within minimum edge between, like that is between two nodes. Then is social network. It's used for transition and finding connections. And web crawling. Search engines use BFS to crawl and index web pages level by level. Then next is network broadcasting. It's used to broadcast message to all nodes in a network, and it have many other nodes like finding connected components, level order traversal trees, and etc. Next, we look at the advantage and disadvantage. Advantages. It finds shortest path in unweighted graphs. It's simple and easy to implement, and it's complete travels of graph of a tree. And if you're looking at the disadvantage, it requires more memory due to queue storage, and it's less efficient for very large graph. And to conclude, we can say that BFS is a fundamental graph travels algorithm that explores nodes level by level using a queue. It's very simple, effective, and widely used in networking, pathfinding, web crawling, and many real world applications. We use BFS. So, I hope you all understand what's BFS and it's how it works and the example and real world application. So, that's all. Thank you.